Hello friends, welcome to engineering tutorial. So far we have discussed some basic concepts related to electrical machines, starting from the basic introductory concepts to electromechanical energy conversion, about rotating electrical machines and other related concepts. So in this video we are going to discuss about an important concept related to electrical machines, especially rotating electrical machines or continuous conversion electrical machines, which is the energy balance equation. So the definition of an electrical machine is that it is a device which converts electrical energy into mechanical energy or mechanical energy into electrical energy. Okay, that is, there is a electromechanical energy conversion. Okay, and this electromechanical energy conversion is it obeys the principle of conservation of energy. Okay, so it means that energy is neither created nor destroyed, it is only transformed, it is only converted. So we know that this electromechanical energy conversion, uh, from electrical energy to mechanical energy conversion, it is done by a electrical motor, and the reverse, mechanical energy into electrical energy, is done by a generator. And the basic elements of the electromechanical system, be it a motor or a generator, it involves three elements. Those three basic elements or components are the electrical system, the mechanical system, and the coupling field. Okay, so this coupling field is generally the magnetic field. Okay, so this is the block diagram for both the electrical generator and the electrical motor. So for electrical generator, the input is mechanical type, be it mechanical movement, motion, force, torque, anything, and the output is of electrical nature, be it voltage or current. The mechanical system lies on the extreme left, the electrical system lies on the extreme right, with the coupling magnetic field in between. For electrical motor, the input is of electrical nature, be it voltage or current, and the output is mechanical, motion, force, torque, any mechanical quantity. So the electrical system lies on the extreme left and the mechanical system lies on the extreme right. The coupling field, which is of magnetic nature, is common in both the cases. Now, the important thing to understand here is that no machine, no device is 100% efficient. It means that all of the mechanical input, in case of an electrical generator, all of the mechanical input will not be converted into electrical output. Okay, 100% conversion is not possible. Similarly, in case of motor, 100% of the voltage or current will not be converted into its mechanical output equivalent. There will be losses. Okay, there will be loss of energy. Okay, so the net energy will be the same in both sides, the left hand side and the right hand side, but there will be certain amount of loss in the machine, be it electrical generator or motor. As per the principle of conversion of energy, it states that the total energy of the system, okay, be it electrical generator or motor, it will remain constant. The total energy, the net energy on both the sides will be the same, but there will be loss. And the principle of conversion, as per the principle of conversion of energy, the energy can neither be created nor be destroyed. It can only be transformed or converted or from one form to another, as I said. So this loss of energy can be expressed in terms of the energy balance equation. Okay, so this is the energy balance equation. So as per the energy balance equation for electromechanical machines, let's say the total electrical energy input be this. Okay, this is the total electrical energy input on the left hand side. Then the mechanical energy output will be, let's say, this much, and the coupling field, the coupling magnetic field will also consume some energy. There will be some loss of energy in the coupling magnetic field and some other energy losses in the device or the machine, be it a generator or a motor. So the electrical energy input, let's say this is the total input. This we are discussing for a electromechanical machine, be it a generator or a motor. There will be some mechanical energy output and there will be some loss of energy in the coupling field, the coupling magnetic field, and there will be some other losses. Okay, so we can express it in this way. Let's say we have an electromechanical machine. The block diagram is represented. It consists of an electrical system, a mechanical system with the coupling magnetic field in between. Let's say this is the total electrical energy input. There will be some electrical loss, then there will be some loss in the coupling magnetic field, which is called as the field loss. Then there will be some loss of energy in the mechanical system, which is called as the mechanical loss. So the loss of energy in the electrical system is called as the electrical loss. The loss of energy in the coupling magnetic field is called as the field loss, and the loss of energy in the mechanical system is called as the mechanical loss. And then after all of these losses, this will be the mechanical energy output, which will be obviously less than that of the electrical energy input. So the efficiency of this machine, the output of this machine is less than 100%. Okay, as I said, no machine is 100% efficient. Output is never equal to the input. The output is always less than the input. There will be some loss. So if we want to elaborate on these losses, the electrical loss is generally the heating, because of the heating effects of electric current, the I square R loss. Okay, the current which flows through any material, the resistance which is offered by that material will cause these losses. Okay, the electrical losses in the electrical system, the I square R loss. Okay, which will cause a increase in the heat will be released in the electrical system. Then we have is the field loss or core loss, which is caused in the coupling magnetic field. This is because of the fluctuating or changing magnetic field. And then the mechanical loss, which is caused in the mechanical system, is because of the friction of the moving parts. Okay, so this is the friction and windage loss because of the moving parts, because the rotating electrical machines have some rotating components, some rotating parts. So obviously there will be friction and windage loss due to those moving parts. So this energy balance equation is applicable for both electrical generator and electrical motor. Now this for motor, okay, for motor the electrical and mechanical energy will have positive values. Okay, for motor the electrical and mechanical energy will have positive values, whereas for generator the electrical and mechanical energy will have negative values. Okay, so these 2 points are very important in this energy balance equation, which is applicable for all electromechanical machines, be it a generator or motor. In that case, for motor action the electrical and the mechanical energy will have positive values, and in case of generator the electrical and mechanical energy, these two values, okay, it will be negative. Okay, so this is all about the energy balance equation for a electromechanical machine. Okay, so Here we have discussed some of the basic concepts related to the energy balance equation of electromechanical machines. After all, these uh, rotating electrical machines convert one form of energy to another. So the energy balance equation becomes very important and crucial to understand in order to understand the exact operation of these machines in a better way. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.